Now let's return to our mass spring dynamics problem. And remember, we had this matrix B. This was the unstable version of the algorithm. And it describes how the state maps from one time to the next. So positions and velocities. Remember, we said that if we calculate the eigenvalues of B, we can determine the instability or lack thereof of this particular discretization. So a few lectures ago, I showed how if we had 800 particles, then this computation takes a while. So almost 4 seconds here. And if n gets even bigger, of course, that time scales up like n cubed, which grows rather rapidly. Now, in retrospect, is 4 seconds a long time to wait or not? Well, you always have to ask compared to what? The whole reason we were doing this was to figure out whether the time-stepping iteration in the dynamics would be unstable. Well, it's actually faster to just go ahead and run the dynamics, especially if we're sparse aware. So here is our syntax for creating the -2, 1, or the 1, -2, 1 matrix as a sparse matrix, so that MATLAB is aware it's sparse and reacts accordingly. So that's A. Okay, we don't even need the identity matrix because we're just working with the vectors themselves, right? So we just go ahead and we evolve the system dynamics for 50 time steps. And because we are using a sparse matrix for A, it's extremely fast. Almost 2 full orders of magnitude faster than the eigenvalue computation. And if we look at the norm of the state vector, we can see it's huge. And that indicates it's probably unstable. So on the one hand, we did gain sort of an underlying mathematical explanation, or a way of quantifying exactly how it goes unstable by using eigenvalues. But as a computational tool, we kind of failed to find something that was better than just running the simulation itself. On the other hand, we could turn it around and say that if what we really want is the eigenvalue of a matrix, the largest eigenvalue of a matrix, then maybe we can just multiply by the matrix over and over again, and that's a way to find it. So in fact, that turns out to be a successful idea, and that's what we call the power iteration. So here's the setup. A is some diagonalizable n by n matrix, and x is just some randomly chosen vector. Okay, so since A is diagonalizable, we can write it with an eigenvalue decomposition. And then the vector x is some combination of the eigenvectors. So we know that this is possible because if A is diagonalizable, then its eigenvectors form a basis. So every vector x has this kind of representation. And we're going to assume here that I've chosen the indices. If I haven't, I can just reshuffle them in such a way that lambda 1 is largest in absolute value. We're going to call it the dominant eigenvalue. And then lambda 2, lambda 3, and so on are smaller. They could be equal to each other, but I really want truly greater than here, not greater than or equal to, in order for this to work. Okay. So then we observe that if we multiply this form for x by A on the left, so we just plug in A times x, then we just distribute the A over the vectors, and each of these can be rearranged, so a scalar can always come through the product and be put wherever it likes. So we can do the A times V1 first, and A times V1 is the same thing as lambda 1 V1 by definition of the eigenvectors and eigenvalues. So we turn what's a matrix vector multiplication back into just a linear combination of vectors once again. Okay, now we multiply by A again. So A squared times x is the same thing as A times AX. So you take an A right, times all of this. So all this goes in here for a times x. And you play the same game. So you distribute the a over the different terms, you pull the scalar constants through, and you again have a times b1, a times b2, convert those using the eigenvalue conditions, and we just get that each eigenvalue is now squared in that expression. So you can see inductively how this is going to work. Every time we multiply by another copy of a, we just increase the exponent on each of those eigenvalues. And so if we factor out the dominant eigenvalue term from the first one, then it appears in the denominator of all the other eigenvalue terms. And since lambda 1 is dominant, then the magnitude of lambda j over lambda 1 is strictly less than 1 for all j not equal to 1. And so therefore, when I take the powers, they go to 0. And so all these other terms drop out in the limit. So they vanish as k grows. And all that's left is some scalar multiple of the first eigenvector. So in other words, as k goes to infinity, this vector a to the k times x approaches something which is parallel to the first eigenvector. So that's a useful thing to know. Now, it would be a bad idea to take the kth power of a. If a is a sparse matrix, then a to the k will be a lot less sparse as k goes to infinity. So we don't want to do that. But this idea of repeated multiplication of a is something we can do. In fact, that's exactly what the code at the beginning of this lecture does for the mass spring dynamics. Now, we do have the fact that that vector runs off to infinity in norm if a has an eigenvalue greater than 1. And actually, if a has all the eigenvalues less than 1, the norm would go to 0. Okay, that could create a problem for us as k goes to infinity. So the best idea is what we call the power iteration, where we apply a and then we renormalize the vector. So, starting from xk, or maybe it would be better to say inside a loop for k equals 0, 1, 2, and so on. So we're starting from x0, that's some initial guess. Okay, so we define a y as a times the current x. We define an alpha k. This is a normalization constant. And if you read that definition of alpha k, it's just finding the largest element of the vector y. Then you renormalize the vector y by the alpha so that xk plus 1 in the infinity norm is going to have norm 1. Okay, and then you repeat that as long as you like. So because the xk in this algorithm is just a constant multiple, a scalar multiple of a to the k times x, okay, we're just finding a bunch of normalization constants as we go, then we find that that vector xk that we're iterating across actually converges to some multiple of the leading eigenvector. Not only that, if we go back up and look at the analysis we wrote down, okay, the terms here that are left, okay, beside the ones that are vanishing as k goes to infinity, of them, this one is as large as any of them, because remember the eigenvalues are ordered from largest to smallest, So that's sort of the largest error term in the whole expression there. So you can formalize that and calculate that the difference between the power iteration vector and the dominant eigenvector is proportional to lambda 2 over lambda 1 to the k. So that means we get linear convergence, so we can formalize that. If we define, so right, the x's are becoming eigenvectors, so that means that if x is close to an eigenvector, then that would mean that y is close to lambda 1 v1. Okay, so we can get an estimate for lambda 1 by taking an entry of y and dividing it by an entry of x. So that's what we do here. So gamma k is an estimate of lambda 1. In fact, gamma k converges to lambda 1 as k goes to infinity, and it does so at a linear rate. That's what this statement says. The ratio of the differences in successive steps approaches a constant, lambda 2 over lambda 1. That's our linear convergence rate. So the smaller that ratio, the faster the convergence. Remember, that's the ratio by which the error is reduced at each step. Okay, so as an example, if we had this 2x2 matrix A, and we chose 1, 0 as our initial vector, well, we put in y0. So that's the first column of A. The maximum value is 8. So the next entry is 8/2 divided by 8, so 1 1/4. And that has infinity norm equal to 1. Meanwhile, we can also do our first eigenvalue estimate. Okay, this happened in the first element of y. So we divide by the first element of x, we get 8 over 1. Okay, so actually this is a terrible example because I've picked an eigenvector, right? So I've actually picked, you notice that this is equal to